Oh, Jesus. Oh, um, quit. Will you get out of there? Here, get away from there. It's fire. Yeah, fire is hot. Yeah, hot. It will burn doggies. No, I don't want love. No, go on. I'm busy. Ah, TJ, come on, buddy. Ah, God damn you, William. Mm. Mm. Oh. Yeah, I wonder what we'll talk about today. Haha. Yeah, we'll pick up on chapter 17, section 4 there. I don't know. Frenzel, the author of the text, but he has a strange order of things sometimes. It's just strange. But we'll be taking a look at something called the phase shifter, and then we'll examine parallel networks with RC, so resistor capacitors, and that'll be kind of what tomorrow's lab will be. We'll continue on with this RC network stuff, and then we'll do some parallel configurations. I might throw we'll see how everything goes. But definitely we'll be working on parallel. The last lab we seen how a series configuration is, and it's a little different set of math. I mean, remember now, what do we focus on in a series circuit? We take a look at the changes, right? So current remains the same everywhere throughout the series circuit, and voltage varies, right? And then we go and look at the parallel network, and we get a little different deal. And that's how to work with this as well. Even with AC, I mean, we still have the variations in current from leg to leg, and voltage remains a constant. So we'll examine that.
And but first we'll go into a little thing on phase shifters. It's a mention in the book just to show you the some of the capabilities, I guess, of these type of circuits. It's an odd one. We won't really focus on this, but let's take a look here. There we go. Yes, the RC phase shifter. So if we look on the next slide with it, you can see it's a series circuit, right, with a resistor capacitor in there. Shows us how to do the math for it. So really, it depends on what you're going for. What he's trying to say is that you're allowed to pick up your output either on the resistor or the capacitor, depending on what your desired output is. Okay. As you can see, your output can be taken across R or C depending on the desired phase shift. Now, from looking at the last lab we did, we seen, right? If you take it at one point to the other, we do definitely see that the sine wave does get a noticeable shift to it. And so this is the type of circuit that you would have, and and so he's just going through, and it's kind of like a finish up on the RC series circuit, if you will. Again, what are we focusing on? We have the math of, you know, with, and of course the voltage is what's varying. And so what he's saying is that depending on what you want, you could see that the VR has a phase shift of 46.7 and the VC has a phase shift of 43.3. So depending on what you were going for, oh, is where you could pick up the outputs at in this case, either here or here. So depending on, again, what kind of phase shift you're going for. And that's really all this circuit's about. It's like the end point. Because then he jumps right into in section 17.5 here, where we look at ecstasy and R and parallel. So think about what we know about parallel, and that those rules still apply, right? Ohm's law is still effective, but instead of like Kirchhoff's voltage law, now we turn around and now we're going to use Kirchhoff's current law because now we have varying currents. And that works the same for AC. And I mean, we still have the previous rules, right? The sine wave, AC charge and discharge, current square capacitor lead the capacitor voltage by 90 degrees. So we still have the capacitor still working the way it's supposed to. So we still have the 90-degree shift, right? When you have a sine wave across the resistor is always in phase with its current. So that rule still holds. That the resistor is more grounded. It doesn't do anything as far as affecting the AC signal. And again, the total sine wave current for a parallel RC circuit always leads the voltage by some angle between 0 and the ultimate is 90 degrees. So yeah, if you ever solve these and you get something where the angle's past, I got 110 degrees, and it's like, no, not in not with an RC circuit, just so the max is 90 degrees on that. So you do have a limit to that. So we examine it, we take a look at. So now instead of using voltage as one of our phasor diagrams, now we're going to use current as one of our phasor diagrams. So we still have the impedance factor where we would have to come up with overall impedance for the circuit. But now in the series circuit, we were examining the voltage phasor, but now we're going to be looking at the current phasors. And notice, same rule of thumb. I mean, so if we look at what our IT total is by the formula here, we see it's the square root of IR squared plus IC squared, right? Still using Pythagorean theorem for that. So these rules do blend together in their respects. I mean, we don't do anything out of the ordinary once we do get used to doing these steps with this, taking Pythagorean's theorem, using the triangle for this, it does become more familiar. And then it's just a matter of recognizing, okay, when do I use this for like a series circuit? When do I use it for parallel? And of course, we're going to go to the series parallel configuration, right? I'm just saying, it's like a spoiler alert. Um, um, no, as we continue on. So the phasor current triangle, all right, very similar to the other phasor triangles. I mean, we still do the same thing. Like I said, we're going to use Pythagorean's theorem to solve. Um, and he just reiterates, stating the same thing again, where as the previous here, where we have total current is equal to the square root of the resistor current squared plus the capacitor current squared. But because they're both out of phase, you can't merely just add them together, right? So we do have the two out of phase going off and forming our triangle. And once that triangle is formed, we revert to trigonometry, right? Okay. I'm glad we're all on the same page. No. All right. So figuring out impedance. Now, remember from resistor networks, impedance for a parallel network, it can be a little tricky, okay? And that still applies here. So one way he's showing you is an Ohm's law variation, if you will. So if we said that, remember Z is impedance. And impedance is both reactance and resistance, okay? So that's what the Z symbol is. So our Z equivalent, or since we have a parallel branches, so if we're going to make a combinational, the way we would do that, we come up with a Z equivalent and just simply have our applied voltage over our total current. So we solve our total current like so, and then we would have the applied voltage, and then we would go ahead and solve it out like that. And here is an example. So in this case, we have a parallel network, one resistor and one capacitor element. We have a VA of 120 volts. Our IT is 5 amps. Here's our phasor diagram to the right here of current. So we would see that, so he's saying there's 3 amps in one leg and 4 amps in the other. So the 3 amps is, red and red. The 3 amps is going down the leg with the capacitor in it, and the 4 amps is going down the leg with the resistor. The resultant phasor would give us a 5 amp total here. So if we had the, and it's a basic thing, right? So if we had 120 volts with the 5 amps, you can do simple math and come up with a 24 ohm equivalent. Now, yeah, and that's the one thing. You notice there is no phase associated with this at all. So here we go a little bit. And again, remember our changes that we're focusing on are going to be our current. So we can see our triangle leg here is IC, right, and IR. And we know what we can do the magnitude here. So if we say, okay, we got these two numbers, we say, okay, well, if this is equal to 14.14, but what is the associated angle for that? So then you just plug it through. In this case, of course, right, the example is always a nice, easy number. So we do the tangent of theta in this case is equal to IC over IR. And in this case, we get a nice even 10 over 10, which gives us 1. And solving through, we get that we find the angle of theta is equal to 45 degrees. See, and this form always sticks through. So we always are going to use the tangent of theta. Okay, in this case, we're going to solve that phasor diagram for current, that applies for voltage and so on. As long as we're doing the same right triangle type thing, this is our type of formula. So this would associate, it really matters as to what values you would have here, whether we're using, the current in this case, or voltage, or if we're using, impedance or something like that. that still comes out to be true, that this style of formula would work for us. And that's how we would find the associated angle for that. Sorry, a little sidebar. And so let's examine some stuff with this and see what our differences are. So the series voltage drops, VR and VC, have individual values that are 90 degrees out of phase. They're added by phasors to equal the applied voltage, right? You never can exceed what your power in is. Your power out has to be what your power in. Excuse me. So we add up the phasors to, and we see that they all equal applied voltage. And if not, go back and check our math. And yes, the negative phase angle. Remember now, capacitors are always going to put us in a negative in that fourth quadrant there. So it's always going to be an associated negative angle because the capacitor purely is going to be that negative 90. But so our differences here in the parallel branch is that we have the resistor and capacitors. And we can add the phasors and also get our, notice that he says positive phase angle. That's an interesting thing. But yeah, we should be able to find the positive phase angle. It should be somewhere between the line current and the common parallel voltage. And again, if we fall outside those numbers, then something didn't quite go right with the math, and go back and check it. Okay. So we take a look at some of the, what our statements are at this point. What are rules that we can state with? All right. And parallel combinations of X and C and R, and these are always measured in ohms. So impedance is always measured in ohms. Even though it's strange, it's still, it's an opposition to our current flow. And so yeah, resistance in ohms and voltage is always in phase with current, right? And capacitive reactance is also measured in ohms, but voltage lags the current by 90 degrees. So then we go down and state some things about our overall impedance factor. So notice our similarities, okay? So he's saying that in the circuit, series circuit, our overall impedance, voltage lags current, becomes more resistance with increasing frequency. And we've seen that by the formula. So we say X of C is equal to 1 over 2 pi FC. So if we vary the 1, we're of course going to change the outcome. And then it becomes more capacitive with decreasing frequency. So, and that's basically how we swing the phase angle. So we change that value, and in effect, one of the results is that the higher the frequency, the more resistive the circuit. The lower the frequency, the more capacitive the circuit. Now let's see if that's true for parallel legs. Well, in parallel legs, voltage lags the current. That's the same. Becomes more resistive with decreasing frequency. Oh, look at that. That's a slight variance. In fact, it's opposite reaction, isn't it? And then it becomes more capacitive with an increasing frequency. So, so one thing is the same, but then as far as where that phase angle would be, it's an inverse, if you will. And that's because of the way the math is from the parallel to the series. And here we take a look at the formulas. And these are available also on the formula sheets that I handed out, that 3-page deal with the little diagrams. These are on that as well. Excuse me. And we see what our variations are, if you will. I mean, X of C is still found the same way, series or parallel, 1 over 2 pi FC. In the series, of course, we're focusing on the voltage changes, and in the parallel, we're focused on the current changes. Our way that we get our overall impedance is different. And notice that in the series, we have to do the square root. And then over in the parallel side, we're going to find an equivalent, not an impedance total, if you will. And then as far as how we find our tangent of theta, notice that in the series, remember it's a minus sign right there, right? So the tangent of theta is equal to a negative x of c over r. And then the parallel side, because we're dealing with the current instead, um, a tangent of theta, notice no negative sign, is equal to IC over IR. So that's like a recap for where we're at this point. This is everything that he's had up to in this chapter. And like I say, tomorrow's lab, yeah, big surprise. We're going to do parallel networks with resistors and capacitors and find out and see how those work. And then we'll have a little, of course, a little calculations to go with that to go through, and then we'll measure and compare. Anyway, so here he's looking at radio frequency and audio frequency coupling capacitors. That's a thing we'll find out as we go through these, that a lot of these applications are used for radio, believe it or not, you know, and our media, if you will, these days, for communication purposes, for broadcasting, sending out signals. And if you got into communication, you'd see why. I mean, a key note is that in communications, low frequencies have greater distance and higher frequencies have less distance. And it's all about, you know, before the signal degrades. So if you were to look at, let's just go old school, right? The original one was, you know, the AM amplitude modulation, AM radio, which has a hell of a distance. It can go very, very far. I remember when I was a kid, we could drive out and a lot of the cars back then, of course, just had, you know, the older cars had AM radios only. You had to buy a special one to get an FM radio. Yeah, I'm old. Um, but we would be able to get an AM station quite a distance outside of Chicago. Whereas, yeah, later on in like the FM, you would start losing the FM station the minute you started leaving the city limits. And the reason is the speed. AM is a lower frequency, and so it can travel a farther distance. And the higher the frequencies you go, the less distance it can go, you know, it can travel. So if you really think about that, now that we're in the use of microwaves and things like that, I mean, ultra high frequencies. So that's why those antennas with them are the associated, those big round microwave antennas that are huge. It's the power. It's the power, because you cannot transmit those high frequencies for a very great difference without a lot of attenuation going on. Anyway, but you get a lot of associated noise, and coupling capacitors, in this case, since Frenzo brought it up, he made me sidetrack. Anyway, so coupling capacitors, in this case, you know, like in a case like this, you would be using that. Yeah, see here, the coupling capacitor is used in the application. Yeah, okay, of a coupling capacitor. Okay. The coupling capacitors, low reactance allows developing practically all the AC signal voltage across R. And so what he's saying is that in the phasor diagram, the tangent of theta for this particular thing, just because of the amount of difference, you know, the 10K ohm to the 100K ohm, as you can see here, most of the voltage, we have 10 volt total, and 9.95 of that is across the resistor. So your phase would almost be with no deviation in a case like this. So because of that factor, and of course the higher up we make the resistor, but you have to be careful, because then you get to a certain point, you make an unbalanced circuit if the degree of impedance is too great between the two components. If one is very much larger, it kind of negates the smaller one. But if you keep it within a range, like in this case, a 10 times range, you're still able to get the effects of the capacitor without dealing with so much of the negative aspects of it, if you will. So it's a way to cheat, still get the benefits of the capacitor without having to deal with the negative aspects of it. But It's like I say, he likes to throw in circuits of how they're used for examples and whatnot. And then, yes, we're going to talk about it because I know everybody was looking forward to this one. So if you remember from the DC side, we did have voltage dividers. Well, that still very much applies to this as well. It's just a little different approach with it. So if we have capacitors connected in series, okay, across this a voltage source, then those capacitors would serve as a voltage divider because the voltage would not, unless they were, identical components, the voltages would distribute evenly. So we would need to find out how it's distributed, right? So of course, each capacitor has part of the applied voltage. And again, see, this the rules from before always apply. It's just, recognizing how we have to apply it. So again, it's just following through with KVL, Kirchhoff's voltage law, right? That the sum of all the series voltage drops equals the source voltage, where it has to. And then the amount of voltage across each capacitor is inversely proportional to its capacitance. What the hell does that mean? Well, that's the formula. If we were to look at, if we look at the capacity of charge, we look at the formulas involved where we figure out, okay, how do you figure out reactance? Well, it is part of the formula and the way you have that set up. So it would be an inverse relationship. Remember that, it's always, but here's a circuit example. Oh, my bad. A circuit example of what he's talking about, right? So capacitive voltage divider, bam and bam. Now remember when we going back to like our God, what was that? Our second lab, I think, where when we have two capacitors in series, what happens here? And think about that because remember now, even though we're dealing with like X of C and things like that, the actual nature of the capacitor itself still remains the same. We still have the capacity to charge. It's still going to have an associated value, you know. So that still does very much come into play. And if you remember, if we had a series, how we had to figure out what the overall capacitance was in a case like this. So let's examine that. So you can see here, okay, we have a 2-to-1 ratio here. And notice that the 2 microfarad capacitor has 40 volts, whereas the 1 microfarad capacitor has 80 volts. So the smaller, and like it said, it's inversely relational, right? If we go back and look, the amount of voltage across each capacitor is inversely proportional to its capacitance. And as you can see, that does hold true. Now, how did that, well, what happens is, and that's because of this formula, see, if we go and look, X of C is equal to 1 over 2 pi FC. So in this case, we came up with, for the 1 microfarad, we have an 80 ohms reactance. And for the 2, we have 40 ohms reactance. And because current remains the same in a series circuit, we have a I total of 1 amp that would get applied to both of those and come up with our voltage for this in this case. Now, we can plug through and use the actual voltage divider, if you will, but he's basically making a statement and showing that, how the capacitive nature works and what we can expect. There are some common things that, like in this case, always remember X of C is going to be an inverse type relationship because the 1 over 2 pi FC. So it always throws it. If it was like, if X of C equaled 2 pi FC, then it would be a direct relationship, and that would change everything, but it does not work that way. But that's pretty much it for chapter 17. And like I say, going through the parallel networks, and then tomorrow's lab, we'll be doing parallels. And let me think. I think I was going to set up Chapter 16's quiz for today. I would like to assign Chapter 17's homework today. And then, yeah, we'll have a parallel RC circuits lab for tomorrow. So we'll examine that, take a look at some of these things. And then that'll open us up for Chapter 18. And we'll dive into that on Wednesday. And then Thursday's lab will reflect that, and we'll keep going with this. But it's pretty straightforward. Like I say, as long as we recognize what the capacitor's doing, what we expect. I mean, we always know that the minute we throw a capacitor in there and we have an AC signal, we know that capacitor is always going to have that negative 90 degrees associated with it. How the resistor reacts. And we know that the resistor does not have a reaction, if you will, where it causes any type of phase shift of any sort. And then our basic rules still apply. I mean, what happens with a series circuit? What happens with a parallel circuit? It's just a matter of how, we do have some changes, of course, because now we have to worry about things like phases and then associated magnitudes, because now things are in a triangle relationship, so we can't merely just add them together or even multiply them together, if you will. But as long as we're able to recognize, what the elements are doing, and then we just apply our associated math, should work out well. And that's why I think that formula sheet should walk us through pretty much most of the rest of this course, actually. But that's really all I have today. It's kind of I know it's a short one, so sad. But yeah, I'll post the Chapter 16 quiz. I'll post sometime, probably within the hour. And I'll make that, 24 hours open for you. So whenever you have time to go ahead and take that, that would be awesome. And then I'll post Chapter 17's homework today, and that'll probably be due, I don't know, Friday or something like that. And then we'll have the quiz on that next week, I think. But that should do it. And then, and then tomorrow, like I say, get ready. We'll do some parallel circuit setups for lab, and that should do it. And yep, that's it. I'm done yapping. Anybody have any questions, or you stop sharing this? Ugh, there. Oh, he's so quiet. See, this is why I like class better, because then I can look around and see faces and stuff. Here, all I see is little sort of like off gray boxes with names in them. But anyway. But no, you guys have any questions? We're all good?
I think we're good.
All right. Well, like I say, keep an eye out on Blackboard then later on today for the quiz and then the homework, and then otherwise I will see you guys about this time tomorrow. A little early. All right, gentlemen.
Alrighty. See you later, Tom.
Yeah, I'll see you guys.
See ya.
Sounds good. We'll see you later.
All right.
See ya.
Bye.
See you, Tom.
Bye-bye.